Hello everyone, my name is Lois. My talk is about graph-based fuzz testing for deep learning inference engines. Fuzz testing is one of the major methods of quality assurance for deep learning systems. However, existing techniques focus on the quality of deep learning models, but lacks attention to the core underlying inference engines. In fuzz testing of deep learning inference engines, the first challenge is to generate diversified deep learning models to trigger different parts of a given deep learning inference engine. The second challenge is to capture the behaviors of each test, such that fuzz testing can be well directed in generating new tests. In our approach, deep learning models are defined as digraphs from nature and effective basis. The model generation involves the following definitions. Digraph. A neural network can be denoted by a digraph. Edges are data flows. Nodes are operators. Subgraphs are applied to define those specified structures. Subgraphs or operators are called as blocks. A block corpus contains blocks and their attributes. The graph-based fuzz testing framework is composed of block chooser, coverage criterion, input mutator, and mutation selector. In block chooser, Monte Carlo Tree Search is used to search the most promising blocks for deep learning model generation. Each node of the tree represents an operator of the block corpus. Monte Carlo Tree Search dynamically adapts itself to the most promising search regions, where good combinations are likely to find more exceptions. We use the following coverages to characterize behaviors of operators. Operator-level coverage is defined as the weighted mean of the set of metrics. The fuzz testing framework applies for model-level mutations and two source-level mutations. We answered the following 6 research questions. Effectiveness of the approach in detecting exceptions. Effectiveness of Monte Carlo Tree Search-based search. Effectiveness of our model. Effectiveness of the mutation strategy. Effectiveness of the subgraphs. The relation between the exceptions and operator-level coverage. Our block corpus contains 50 TensorFlow operators and 3 subgraphs. Our experiments are conducted with MN on x86 CPU and ARM CPU. The final status of the test process includes model conversion failure, inference failure, data comparison failure, and data comparison pass. In order to answer RQ1, we generated 1,000 models and found more than 40 different exceptions. Some typical exceptions are shown as below. Various exceptions are detected in model conversion and inference process, such as crashes, inconsistencies, not a number, and infinity bugs. The table shows operator-level coverage, exceptions, and duration under different block numbers for RQ2, 3, and 4. For RQ2, the Monte Carlo Tree Search-based search outperforms the random-based search in boosting operator-level coverage and detecting exceptions, as shown in the first and fifth rows. For RQ3, through applying the ARM model, more exceptions for each strategy can be detected, as well as operator-level coverage increased, as shown in the second, third, and fourth rows. For RQ4, our mutation strategy is useful by up to 8.2% more operator-level coverage, and 8.6 more exceptions detected on average, as shown in the fourth and fifth rows. In order to answer RQ5, 100 mutated subgraphs are generated to evaluate the effectiveness of 3 subgraphs in block corpus. The main type of exceptions is state comparison bear on ARM CPU. For RQ6, the exceptions detected are all within the scope of operator-level coverage. The single-edge coverage is usually associated with input degree coverage or output degree coverage. To overcome the challenge of generating deep learning models with diversified combinations of operators, this paper employs a novel graph-based fuzz testing method. The method is universal, and the MN-based implementation is just one possible application scenario.
Hi, welcome everybody to this session on deep neural networks quality assurance. Now we are in the Q&A for the first paper, which is entitled Graph-Based Fuzz Testing for Deep Learning Inference Engines. You've already seen the video, and we have here one of the authors, which is Wei-Si Luo, who will be answering your questions. So I already see in the chat that there are 2 questions. If you have any other question, please use the chat. So we have one first question by Theodora. And the question is, are the input mutations different for different type of blocks? Or is your approach a completely black box fuzzing approach? So, what do you see?
Different blocks. Different.
She's asking if the input mutations, if they're different for different types of blocks.
Different blocks. We conducted our conducted our experiment and our block corpus contains 50 TensorFlow operators and 3 subgraphs.
Mm-hmm. And I think what Theodora is asking is if these input mutations are different for the different types of blocks. I mean, actually, what she wants to know is if your approach is black box, in the sense that you don't see what is happening inside, or if
yes.
you can see. So it's black box.
It's black box. Yes. Yes, indeed, it's a black box, but deep learning inference engines, the workflow of deep learning inference engines are similar. The implementation, the workflow contains model conversion, model optimization, data perform conversion, and so on. And they are familiar.
Okay, so if you look at the chat, then there is a clarification by Theodora, because she says, I think you mentioned that the graph structure has different transformations, for example, conv2D or add, etc. How are the mutations generated for these?
Different For convolution 2D, the fast testing framework applies for model level mutations and two source level mutations. The question is convolution 2D. The mutation, the source level mutation will change the input tensor shape and the parameters of the operator.
Okay, let's see if Theodora has further questions. If not, I'm going to go to the other question from Xia Yu. Theodora says it's fine.
Could you please type the question on the chat?
Yeah, Xia Yu already typed the question. He asks, how do you calculate you found in the deep learning with the deep learning engine? Are they confirmed by developers? So you found bugs and you give amounts, the amount of bugs you found. How did you calculate those, and if they are confirmed by developers?
The details, the details contains the log. Sometimes we made a smaller model to check the wrong operators.
Okay. And here, did developers confirm the bugs you found with your method?
Sorry,
the thing is, if the bugs, the number of bugs you've calculated with your method, if it has been confirmed by real developers.
Confirmed by real developers.
Yeah, the thing is, did you ask developers if your results are good? Did you do that? Did you ask developers who write code and tell them, look, we have these results, can you confirm them?
We didn't confirm the bugs to the MN's developers, but we can but we can check the result and confirm the result is different from the widely used framework TensorFlow, and
Okay.
the result is different, and some crashes details printed in the log.
Okay, thank you. Let me make another question. I put it in the chat so that you can read it as well. What would be the next steps in your research?
Maybe security in deep learning inference engines. You use fast testing method.
Xiao Yu asks you if, and this is related to my question about if you consider implementing your method in the industrial field to form a complete tools for deep learning libraries and frameworks. Have you considered that?
Yes, it works in industry deep learning inference engines. The method is used in our company. Use the internal build in our company.
Okay. Are you going to release
and many bugs founded?
But it's not publicly available as open source software. It's internal for your company, is it?
Yes. The code is not open source.
It's not open. Okay, thank you, Weisi. So we still have 10 seconds to go. The next presentation in line is robustness-oriented testing for deep learning systems. We will see you in the next Q&A with the authors.